This is a follow-up video to double slit experiment in magnetism, both wave and particle. And it is for a follow-up paper. Magnetism, further proof of wave-particle duality. And I'll read that out to you. The abstract. This paper was written in order to confirm the results that were received in the experiments that took place that led to the paper Magnetism, Insights from the Thomas Young experiment, where it was concluded the magnetic phenomena is both a particle and a wave. Will different interference patterns conform a KHUMSON and wave-like behavior? The KHUMSON being the name of the particle associated with magnetic phenomena. This paper concludes by confirming what was discovered in the mentioned paper. And the setup of the experiment, if you remember the original experiment, we'd set it up like this, with slits coming out like this. And we got all sorts of different results. This paper, we are using slabs like this, 2 of them, and you have them apart, or this freaking phenomena. You have them like this and like this. So we're using slabs, and here the slabs we're using, like in that setup. So we did the same thing with the slabs. We measured the magnetic phenomenon across the face of the slabs, across the face of the slabs. You know, there'll be 2 slabs like this. So we measured across the face of the slab. And it was a much stronger magnet than that. This is at home, and would measure across the face. So we would create an interference pattern, and then we'd see what we get. And we would have them 3 centimeters apart and 1 centimeter apart. And we got results like this. I mean, all the results will be given to people. As you can see, at 0.5 centimeters, we got this dipping phenomena. And when you move a centimeter away, we started getting, this is with the slabs 3 centimeters apart, a wave-like formation. And by the time you're at 5 centimeters, and now it's expected you get a wave-like behavior. And here it is at 0.5 centimeters. There's the phenomena. There it is at 1 centimeter. It's almost already a wave. At 1 centimeter, I mean, that's very quick. Last time we were getting it into a wave after 2 centimeters, 3 centimeters. So it depends on how you interfere it. And then we did the same thing with the slabs. Instead, they were 1 centimeter apart. And this is what you got. This is the data you got. This is at 0.5 centimeters. You got this, and as you moved away, you started getting a wave. But at this time, at 1 centimeter, it wasn't a wave, and so you're getting this. So we're comparing the wave patterns. The slab 3 centimeters apart, and slabs 1 centimeter apart. See, with when we had the slabs 1 centimeter apart, it didn't become a wave. It took, and at 1 centimeter away, it's still not a wave. The interference is, but when we had them at 3 centimeters apart, within 1 centimeter, it's a wave. That's very quick, because we're expecting 2 centimeters, which is 2 jiffies of a second, which is very fast. And then, but just to satisfy our curiosity, we decided again, to vary the experiment. We decided to put the things like this. We had a formation like this, you know. So this is varying the experiment like this, and we would put a slab at the back to try and balance just different things. We're trying to see what we're gonna get. You understand? With all the, do we still end up with that wave particle behavior? Just before we move on, you can see at slabs 3 centimeters apart, one and you can see the wave-like formations after 2.5 centimeters, after 5 centimeters. So now what we did is, and we put the slab on with the metal slabs. This is what we got with the metal slabs. You know, we're putting that metal slab at the back at 3 centimeters apart, and we wanted to do it again, you know, and you got that interference pattern, and then you started getting the waves. 2.5 centimeters from phase with the slab. So we didn't bother doing it 1 centimeter apart, because we're going to get this KHUMSON is confirmed. So the paper, I'll read to you our conclusions. This paper confirms what was observed in the paper Magnetism, Insights from the Thomas Young Experiments, for the same reasons. One can see with the interference, the phenomenon behaves differently the further away one moves. This is because the phenomenon organizes itself into a wave. It was confirmed in a more dramatic fashion because of the nature of the interference. We could see at some parts that between 0.5 centimeters and 1 centimeters, this is 1 jiffy of a second, the phenomenon has organized itself. I mean, this is incredible calculations, faster than any quantum computer. By taking this wave formation, it can only mean it interacts with some medium that it is going through. All quantum phenomenon does, whether this medium is ether or dark energy, dark matter, I don't know. But there's some medium it is interacting with, that's why it's taking that wave formation. As so much of this stuff disappears so quickly, there is only possible explanation is it is highly unstable. With 2 to 5 jiffies, 90% of this phenomenon has disappeared. Thus, the magnetic phenomenon allows us to understand both the stable quantum material like photons, neutrinos, and electrons, as well as highly unstable material that disappears in jiffies of a second in colliders. So this magnetic phenomena is in between these two, between the stable and the unstable quantum phenomenon. This experiment once again goes to show the reality of knowledge, that we can only know what is discrete and everything is in a relationship, not forgetting the original law that led us to understand that everything is in a relationship, the law of consistency. The magnetic phenomenon must be consistent with all other phenomenon at basic levels. So that is the reality of the magnet, and you take it as what you like. You want to fight with data, you don't want to fight with data. The KHUMSON, as far as we are concerned, is confirmed. It's a particle and it is a wave. It organizes itself no matter what you do. So our next experiments will be bigger. We want to in a lot of data, much more than this, more data than has been collected so far, as we know, in magnetism in this manner. And that's what we're going to be doing from now on. So next week, a week from now, we'll put on this new because the experiments are already done. We're just waiting for the papers to be published. So, well, this is the face that discovered a KHUMSON. So if it makes you happy, if the face scares you, that's up to you. You do what you like. We don't care. We're moving forward, and the magnet you're going to see great things. And you won't be able to understand magnetic interaction if you do not understand that it is a particle and a wave, because the next experiments will be clashing these things. There'll be particle interaction, and if you will just be amazed, and you'll be lost, and you'll be talking stuff that nobody you'll have to go and study it with electricity. That's where you belong. You won't, because you can't understand it as a quantum phenomena. It's electromagnetic phenomena. There's electricity and there's magnetism. Electricity comes from a particle. Magnetism comes from a particle in the electromagnetic effect. Thank you very much. And there it is. That's it. Always organizes itself into a wave. No matter the interference, it will be disorganized. It organizes. It's not a blob. Don't be a crybaby. It's a KHUMSON. Get used to the name. It didn't come easy. It came with a lot of work. Goodbye. Thank you.